פשוט. אחד פה ואחד פה. Okay. Welcome everyone, both to Electroengineering, to the Technion, and to the ACRC, which is Advanced Circuit Research Center. I'm very happy to open this workshop. I think the subject of this workshop is something that puts together everything that electroengineering is about. There is physical aspects, there are mathematical aspects, there are circuit aspects. It's a long-term visionary area, high risk, which means high probability of failure, everything we really like when we do academic research. So I welcome you here. I hope you have an interesting day with a lot of challenging questions and a lot of interesting thoughts. Enjoy the stay.
This one works? Okay. It's a great honor to invite our keynote speaker, Professor Steve Kang. He's a distinguished chair professor in the University of California in Santa Cruz. He has been the head of several departments in electrical engineering. He also spent a long time at Bell Labs. And most important, he has been the first PhD student on the topic of memristors. So, Professor Kang, please come forward to the podium.
Yes. We have a clips.
Okay.
And the second side. Yeah, now we are
Right in the pocket.
dance.
And I can use this one to advance, right?
Now we will put.
Yes, yes. Okay, thank you. Good morning. Glad to be here. I thank organizers of this meeting, and my wife and I, we've been traveling before this meeting, and we will be leaving on Friday, but we've been thoroughly enjoying our visit to Israel, and highly impressed by really nation building in Israel and the younger generation especially. So today I'd like to speak about memristor and for engineering purpose, how they can be used for different applications. And I am personally very grateful that many people do have interest, because I believe when many smart people get together, something new will happen and more good things will come out. So that excites me a lot. In terms of outline of my talk, I understand I have about 55 minutes. So we will try to abide by that time. The memristor itself stands for memory resistor. It's the short name for memory resistor. Transistor, itself is a short name for transfer resistor. So somehow resistor plays a very important role in electrical engineering or electronics or even modern IT technology. So we will briefly go over Moore's law and where we are heading. Great visionary Richard Feynman, what he said about this nanotechnology, which makes everything very exciting. And then memristor and memristive devices. So people do have some discussion on, is it really memristor? Is it not memristive device, and so on. So we will visit that issue and have some maybe discussion on that. And personally, more interesting aspect will be, what is the potential application of memristive devices or memristors. And then what good thing will come out of it in the future. So that's the sort of outline of my talk. So let's look into the sort of a history, modern history, starting from invention of a transistor at AT&T Bell Labs by Badin and Breton, who worked on the Bill Shockley. And even transistor itself, people do argue, you know, were they really the first one who invented the transistor? Wasn't there some other people and so on? I think there was some other outstanding contributions, but somehow they realized it and they got Nobel Prize and they became very successful. And thereafter, Jack Kilby, another electrical engineer who got Nobel Prize in physics. I always thought in order to get Nobel Prize in physics, you have to be physicist and you have to have a PhD in physics and so on. He broke the rule to some extent. He was electrical engineer, happened to be University of Illinois graduate where I had been department head. So I had the pleasure of meeting Jack Kilby. And in fact, the year that he got Nobel Prize, we suddenly as department head we realized we didn't recognize him as a distinguished alumnus. So September 15, we gave a distinguished alumnus award. And the same year, on October 15, he learned that he got Nobel Prize. But I think Jack Kilby really had a great contribution. If you look at the second picture in the middle, it's an ugly picture, you know. But the concept, although it was simple, was a very, very good one. Why just do everything together instead of making individually and then try to solder them together? So he came up, and my lesson to young people have been always, his boss at Texas Instruments, actually he had this idea when he was in Wisconsin, but at the Texas Instruments, his boss kept telling him that don't bother to work on it, it wouldn't work. So don't work on it. And he had to sneaked into his lab on a holiday and made this happen on that holiday. So as a teacher, my personal philosophy has been always, I try to be very, very careful when I talk to young people that it's impossible or don't bother to work on it. You know, they can be much smarter. And one of my colleagues said, I am successful professor because now I proved my students are better than I am. So I think that's the joy of being a professor in a university. And then the other important thing is at AT&T Bell Labs, Kang and Atala, Duan Kang, whom I have known very well, his boss Atala, they made MOSFET, which made integration happen. I mean, if we had a bipolar technology only, probably we wouldn't be where we are. So there's a lot of good things to come out when a lot of good, smart people work on it. And this is a sort of past history. When I was at AT&T Bell Labs, I worked on Bell Mac 32, the world premier CMOS 32-bit microprocessor chip. These days, even graduate student, undergraduate student will design this thing, you know, overnight. But at that time, it was a huge project. And in fact, when US stamp was 8 cents, they celebrated this achievement. This Bell Mac 32 chip, they put the picture on US stamp. Now US stamp is 44 cents. So that's when it was 8 cents. So it's part of history. So if you look at the progress we made through integration, it's tremendous. This first picture shows how the computation power is increasing per cost year after year. I think it's mainly through integration technology. So the bottom picture shows Intel's 10 micron, the Intel 4004 4-bit micro chip. You know, it had only 2,300 transistors. It was a huge success. And then by 1999, it's only 30 years later, you have almost 10 million transistors in it. So if you look at the progress made, it's more than 4,000 times over, you know, almost 30 years. It's increasing in terms of packing density twice every 2.3 years. But what is even more interesting is beyond Pentium 3, which was in 1999, and Xeon, the Harlem chip in 2010 or thereafter, which has 2.3 billion transistors. So if you look into that thing, say 2010 and 10-year period, right? So you have increased over 240 times, and it's 2 times every 1.4 years. So you can ask, how can it be? There's so much problem in integration, and it's mainly due to embedding of more transistors, actually. So maybe they had to handle maybe on this less challenges in interconnects because memory is very regular. But that also shows the importance of putting more memory into chip. So it brings some significance in Memristor because it's supposed to be resistive with memory. And if you look at the data rate, storage technology demand in the future is tremendous. I think we take pictures with a cell phone. You have a 10 megapixel. We send pictures, and then you have to store it somehow. This storage technology need is increasing year after year. So that's very interesting. This is from Semiconductor Research Corporation, a very famous this sort of a projection. So you have horizontally more than more, so sort of what type of application you have: analog, passive components, high voltage power chip, or sensor, and the bio chips at the end. And then vertically, you have a technology scaling toward the 22 nanometer or even below. People always have been saying that, it's not possible to go below certain limit and so on. People say not possible below 10 nanometer. Who knows? I mean, it may go below 10 nanometer. The message is there are so many smart people working in this field, and the Moore's law is somehow exerting some kind of a good pressure. So when people say, I cannot really do this, then they scratch their head. Well, according to Moore, we can do this. Somehow some smart person finds a solution, and then there is a next progress. The other important thing is, including E.B. Friedman, people are now looking into three-dimensional integration. Okay, if you cannot shrink horizontally anymore, how about building high-rise building like in Tel Aviv or some other place? You can stack up the chip to put more capacity into small area. Who cares? As long as you have lots of things happening in small area, it's still winner. Although there are some other challenges as well. But what is important is, in terms of the projection, in fine technology, nanotechnology area, the high-value systems such as biochips or biomimetic chips or neuromorphic chips, I think that is very exciting. We tend to live longer, and we lose memory, and we may lose some function. Can you implant your chip and make up for it? And there are a lot of progress being made. It may not be mass production for major industry, but it has a value in it, and that can be good contribution. Back in 1960, when Richard Feynman was giving lecture, he said there is plenty of room at the bottom, meaning that when you scale down, you can do a lot of things. So if you look at the bottom, storage technology, computation, manufacturing, medicine, like a biomimetic chip, that type of things. So indeed, when we get into nanotechnology, I think there's a lot of things we can do. And even people try to make MEMS and NEMS, and then try to make memory component out of it. Some work is going on at Berkeley for that. Who knows? I mean, there's a lot of good things we can do. And even when I was at the Bell Labs, people in charge of research, they've been saying that we have done all the research that can be done, and it's only application. They were deadly wrong, in fact. So science is progressing. And the electrical engineers introduce new tools, and then we find another great findings, and then we keep ongoing. I have a friend in chemistry at the Santa Cruz, David, and he found some life in ocean where this water is boiling, but he found the bacteria in that. People said it's impossible, but he found it. So, all these things that we find, and it opens up very interesting opportunities. This picture shows actually the tetrahedron picture that you are seeing is original picture introduced by Leon Chua, my teacher, my professor at UC Berkeley when I was a graduate student. I got to Berkeley in 1972 and met Professor Chua. And he just published this paper in 1971, which got the field sort of excited. I didn't know much about it. He said, would you be working on this one? And I, as a graduate student, I said, yes, I would be, but I had a doubt what the use of this would be. So I naively, as a naive graduate student, asked him, Professor Chua, if I work on it, would there be drop? And then he laughed and said, whatever you do, if you do with good quality, there will be drop available for you. But I really didn't know what the application would be. But concept is rather interesting. In electrical engineering or in physics, we always talk about the voltage and the current, top and bottom, which is linked by Ohm's law. I mean, linear relationship can be nonlinear. You can have a V is equal to, say, function of I, which is nonlinear. Like a diode is nonlinear resistor, for instance. Then you have a flux linkage V and the charge Q that we are familiar with. So you do have a relationship between, actually this chart shows very vividly, between voltage and current you have a resistive relationship. Voltage and flux you have an inductive relationship. Voltage and the charge you have a capacitive relationship, C is equal to CV, but it can be nonlinear as well. But his question was, what is the relationship between P and Q? So he thought that was a hidden link because people always look from the front side. So that edge is sort of hidden and the people didn't pay attention. So he said, what if there is a relation? P is equal to nonlinear function of Q, FQ. But it doesn't make much sense physically. What is it? But on the other hand, he realized if you take time derivative on both sides, dphi dt is a voltage V, and then if you take a derivative dphi q dt, you can have a sort of a two-step, dphi q dt, dq dt, where dq dt derivative of charge is a current. So that slope function must be resistive in nature, resistor. But it's a function of Q, which is the integral of a current. It is like an accumulation of how much current you have received. So its history is in there. So he said, okay, this must be resistor with history, memory. So that's a memristor. So it made a good sense. And then he published the paper in 1971. And I think Berkeley people, in fact, liked the paper. And then Charlie Dussault, Unico, they recruited Leon Chua out of Purdue and became faculty member at Berkeley at that time. So that's a sort of a past history. But there are a lot of smart people. I earlier mentioned about transistor invention. They were really the first one who worked on transistor. If you go back to history, there are a lot of other people, 30, 40 years back, even prior to the invention of a transistor worked on it. This, as I prepared the talk, I sort of found a paper written by Neil Arthur. He's a physicist. He published this short communication in 2008, Nature, October 2008. So this on the bottom, you have a Nature 455, which was published October 30th, 2008, after HP announced the memristor sort of invention. And he's saying that DQ-dphi, that relationship, existed and found by physicists. That was a work of S.L. He. He was a doctoral student at Harvard in physics. And the advisor Blombergen, who has been sort of predicting that there should be some relationship. And in his paper, in their paper in 1965, they published this chart, which shows a relationship between P on the left-hand side, although expressed in the voltage, but you can shuffle the equation in terms of P, which is the electrical quantity actually. You see, so dp/dphi, where P represents the electrical polarization and H applied magnetic field. So That is horizontally you have the DC magnetic field. And they did experiment and found this linear relationship. And then they also said it could be nonlinear. So I was glad to find this paper because physically they did prove that there is a relationship. And they made some crystal. In fact, the title that NiSO4 6H2O4, that's crystal. And they did a measurement in very delicate environment and did a measurement on that one. So that's very exciting because that shows that physically there is a relationship. Now, getting back to Chua's 1971 paper, he said phi is equal to function of Q can be, or Q can be function of phi. So say, let's take one equation, phi is phi Q. But then when you take a time derivative, the property is voltage is equal to mx. In this case, x is Q multiplied by current. It's Ohm's law, where resistance M is a function of charge. So that was his original paper in 1971. As a graduate student, this was a part of my thesis. I wrote my thesis. Chapter 2 was on this generalization of memristors. So Leon said, let's make it more general class. So we did that. So we said, okay, voltage can be resistance multiplied by current. That's Ohm's law. Still can be two-terminal device. But its resistance can be function of a lot of different things. Not only state X can be function of a current or input. And if it is a time varying, it can be function of a time t as well. And where dx dt, x is now vector. So you can have a variable, many variables, state variables, which is a nonlinear function of xit. So as a graduate student, I looked into this one. Another interesting observation was in modeling, which is known to be mother of engineering. I think that's how we operate, right? When you design certain things, you have a transistor model which help you to design integrated circuits. So we do use a model a lot. A model indeed can be mother of engineering. If you have no good model, then it's not good, whatever you do with that model. If you have a good model, you can come up with a good design. So as a graduate student, I was interested in dynamical system to come up with the models. And I looked at all the books, and not many books written on this topic. But I found in Evans Hall on Berkeley campus, in math library, a title called Synthesis of a Dynamical System. This was exactly what I was looking for. I was so delighted. I opened the first cover sheet, and it says, this book is dedicated to my wife. That's very natural, right? A lot of us do that. A dynamical system, underneath it says, a dynamical system that cannot be synthesized. So it was a very moving statement at that time. But if you look at really many models which can be described by equation in that box. Fluorescent lamp, if you look at it, it's a memristive device. Because you can model voltage-current relationship using this type of equation. The thermistor is another example. And then I found also Hodgkin-Huxley model introduced by physiologists, for which they got Nobel Prize. There are some ionic channels in it, and those ionic channels are memristive. So it's very interesting, in fact. And in fact, there is a similarity. If you look at the ionic channel, I will describe later on. It talks about the probability function between 0 and 1. That is exactly what the HP people also talked about, variable between 0 and 1 in their model. So a lot of smart people think similarly, actually. So that's very encouraging. So after 2008, the HP people announced the finding of making of a memristor in their lab. I was asked whether I can help Leon and Stan to organize a symposium. I was chancellor at that time, in New Baby campus, so I had a lot of important things to do. but I decided that I can help. So I organized a symposium with National Science Foundation funding, Memristor and Memristive Systems Symposium in November 2008, which we repeated in 2010. And the left picture is a famous picture that sort of a crossbar array made by HP people. And the bottom one is a sort of a cartoon that shows application. If you make a device with a memristor, since it will remember, you unplug it and plug it back, it will go back to exactly the same state. You don't have to reboot your computer when you have such a thing. So it has potentially some important applications, right? The more interesting thing is Professor Rainer Wasser. Some of you may know. He is at Aachen University. He sort of said, as a device physicist, materials scientist, he said a lot of things are memristive devices, in fact. So he lists all these different things: nanomechanical memory, phase change memory, thermochemical effect, balance change effect, electrochemical metallization effect, electrostatic effect, ferroelectric tunneling, magneto-resistive memory effect. In his analysis, it can be described by memristive systems equation that I introduced in earlier. Does that mean we invented those things? No. I mean, a lot of smart people did that, but can be modeled, it can be put together as sort of a class of devices through which you can bring lots of smart people into one place and have some healthy dialogue. As Adam mentioned earlier, electrical engineering, with a lot of integration of device physics and computer architecture and materials, a lot of different things. And I think that is a good thing. That is a blessing that happened through what HP did. Because people argue that, we made the phase change memory even before HP. So, does that mean that phase change memory is a memristor, for instance? Doesn't have to be, but it's a memristive device. It shares certain properties, some good applications. You can bring people together, have a good discussion, something good, especially younger people. They are very smart. They will find something very exciting. So in fact, last night I met Shahar. He showed his PhD thesis proposal, which is based on memristive devices. So I am really moved by it, very excited for what is happening now. So in terms of switching, how switch happens in memristive device. So this comes from Rainer Wasser's explanation. So there are different mechanisms. The leftmost one is a phase change between crystalline and the amorphous, the chalcogenide, the glass, and that can be modeled using memristive equation. The middle one is a sort of a intrusion of a metallic filament. See? So, if you give some input, then it grows and touch the bottom, forming a channel, which is actually very close to what actually the right-hand side is what very close to what HP people did. But there is a silver electrode forming and then touching and become the conduction channel, and then when you reverse bias it, it moves back and off. So on and off type of a thing. And then metal, the oxide type of a thing on the right-hand side. So there's a thing which forms the missing oxygen atom when it becomes bigger and bigger, and they intrude, then it can form the channel, and then you have on. When you do it reverse, then it's off, on and off type of a thing. So there is some interesting physics behind it, and the people have done numerical simulation using physical principles, and they can do that. So you have a bipolar resistive switching in transition metal oxide. People have made some sandwich structure, and then they made this characterization, voltage current I. So you have a low curve, right, flat, that's off. When it's on, you have a high current, right? But there is a switching between high and low, back and forth. So that is interesting. In fact, many people are using it. This is HP memristor. Earlier I showed you that top left picture. and then the device structure.